Welcome to the Monty Hall problem. In this video, we'll be tackling this famous mathematical brain teaser which has confused so many people around the world, from average people like myself to PhD level mathematicians. The problem was originally posed by a statistician named Steve Selvin in 1975 in a letter to the scientific journal, The American Statistician. The problem is based on the game show Let's Make a Deal and named after its host, Monty Hall. To understand the problem, let's see how the game is played. Here we have the host, Monty Hall, and you, the contestant. Before you are 3 unopened doors, behind one of which is the prize, a brand new car, and behind the other 2 are goats. You're asked to pick which door you think the car's behind. After you pick a door, Monty, who knows where everything is, opens another door to show you a goat behind it. He then asks you if you want to switch to the third unchosen door or stick with your initial choice. So the question becomes, do you stay or do you switch? Which choice will increase your chances of winning? Go ahead, pause the video and think which choice you'd make. Now what happens is that most of the time, contestants will remain with their initial pick instead of switching because they see the 2 unopened doors and believe the odds are 50-50. Thus, there's no reason to switch. But in reality, in most cases, the car will be behind the third unchosen door. This is the paradox. You're twice as likely to win if you switch to the unopened door. In fact, you have a 2/3 chance of winning the car. But why is that? We can explain it in 2 ways. The first, a mathematical way, using conditional probability, and second, by using a decision tree. The first proof we'll take a look at is a proof using conditional probability. Let's assume we have 2 events, A and B. Let A be such that the car is behind door 1, and B be such that Monty opens door 2 to show the goat. We'd like to see what the conditional probability of A given B is, i.e. this. Let's break down each component of our equation. The probability of A is the probability that the car is behind door 1 before Monty reveals anything. This is always a third. The probability of B given A is the probability that Monty will reveal a goat, given that there's a car behind door 1. It's important to remember that Monty will always reveal a goat, no matter what. So the probability of B given A is simply 1. The probability of B given not A is the probability that Monty will reveal a goat, given that there isn't a car behind door 1. Again, Monty will always reveal a goat no matter what, so this simply becomes 1 as well. The probability of not A is the probability that the car is not behind door 1, which is 2/3. Now that we know this, we can work out our equation for probability of A given B above. Now that we worked everything out, we see that the probability of the car being behind door 1, given that Monty reveals a goat behind door 2, is just a third. So why should this matter? Well, we know that the car has to be behind either door 1 or the unchosen door, door 3, and since we calculate that the probability of it being behind door 1 is just a third, then it must be the case that the probability of it being behind door 3 is 1 minus 1/3, which is 2/3. Therefore, you're twice as likely to win the car if you switch to the third unchosen door. The second way we can prove this result is by using a decision tree. We start again as usual with your initial pick of a door. You'll either choose a car or one of the 2 goats. You're equally likely to get a car as you are to get a goat, which is a third. Now it's Monty's turn. Again, this is key to remember. Monty will purposefully reveal a door with a goat behind it. If he didn't know where everything was and just opens the door at random, then our problem changes. Now you have a choice again, remain or switch. If your initial choice was the car and you choose to remain, then you will get the car, but if you switch, you'll get the goat. If your initial choice was a goat and you choose to remain, then you will get the goat, but if you switch, you will get the car. Therefore, you can see that by switching, you increase the likelihood of winning the car. So the best strategy is to switch when given the choice. Now that you've seen how the game works and 2 proofs behind the solution, try playing the game and testing the odds for yourself. This game is also a neat party trick if you ever want to fool your friends. Hopefully this video helped you in understanding the strange paradox of the Monty Hall problem. Thanks for watching.